welcome to another video where today, apparently, relativity of simultaneity, or however it is that you pronounce that in English, apparently is false, which is interesting because I got that taught not only in my bachelor's degree of physics, but also in my master's degree of physics, and astronomy, both as well. So apparently I must have understood something wrong, or the dude here from Space Edits, who I believe is, or Audits, not Edits, I'm sorry, from Space Audits, I think that's Ellen, has something wrong, which I think is the more likely explanation, or he deserves a Nobel Prize. We shall see.
So, the train example, right? Suppose we got a train moving at velocity v, it's full of passengers, it's got a bomb at the center of the car.
Why I don't understand why he's doing that with a bomb. Typically, it's like a sensor. I think a bomb is a little unnecessarily harmful, but sure, I guess.
Bomb is configured to detonate when it receives a signal from two sensors, which are in the front of and behind the car. So it needs to receive the signal at the same time for it to detonate.
It's equidistant from the center is what he's trying to say here.
And the sensors to transmit the signal are in front of and behind the train, and the train is traveling at speed. Right, the signal will be triggered when lightning hits both sensors at once. The bomb in the middle of
the signal, not lightning.
The train has a wireless receiver. Right, there's a stationary observer on a platform. At the exact moment the bomb-carrying train intersects with the stationary observer.
So when the bomb or the center of the train and the observer are on the same line, kind of.
Lightning strikes the front and the back.
The signal is sent out in the front and in the back
of the transmitters simultaneously, right? So exactly at the same time.
We will talk about what simultaneously means in physics, actually, because it's kind of a complicated thing if you think about it clearly.
As per the requirement, lightning hits both of the transmitters. So
I don't know why he's talking about the signal and lightning like at the same time. It seems kind of unnecessarily complex, but sure.
According to relativity, a lab frame is not necessary as all frames are equal. Right? So
no, that's not what relativity says.
According to the stationary observer, who's sitting in the middle, who has a valid frame, right? Who is just as valid as everyone else's frame. According to him, will the receiver on the bomb receive the signal from the bombs? Again, it's traveling at speed, so it's traveling faster this way, and these are traveling at equal speed towards it, right? Will the receiver on the bomb receive the signals from both directions simultaneously, or will the signal be delayed in either direction? In actuality, will the bomb detonate? Or is there a temporal divergence due to length contraction and time dilation as a function of the square root of the train's velocity over c? In short, are the passengers saved, or does everybody die? Does the bomb detonate? Remember, wireless receiver, motion, train in motion, signals transmitted at the same time. What happens according to relativity? Well, in the lab frame here on Earth, where measurements can take place, the bomb fucking detonates. Everybody on that train dies. Of course it does. Of course it does. It doesn't matter that this person's frame is experiencing this differently as to an actual frame. The lab frame means in reality, in the objective frame of reality, it explodes every time, guys. Every time it.
I love how like the evidence is. Of course it does. Don't be silly. Like that's the amount of argumentation that happens in a flat earther's head. Is does it do that? And then there's no step in between, no careful consideration, no calculations, no models, no nothing. It's just, of course it does.
Explodes. The moral of the story is, no matter what frame you think you're in mathematically, in the lab frame, it explodes. Relativity is retarded. Don't.
It might seem that way because you have fundamentally no clue about it, and I will now talk about it because it's easy to look at a flat earth video and say, well, they're dumb, like I did last week. I hope, I don't know in which order I will be uploading the videos, the one with Venus, right? So it's easy to point at them and say that you're dumb, right? Which needs doing sometimes, but today I thought we'd actually learn something, right? So, relativity of simultaneity, or however it is pronounced in English, that's actually a more nuanced and complicated topic, somewhat unsurprisingly. Let's say, what do we mean by simultaneous in everyday English? Well, let's say you have two people, Bob and Alice want to drop a stone at the same time, right? So Alice sets a timer on her phone for 10 seconds, and as the phone rings, both drop the stones. The That was what we would call in everyday English simultaneous. And I have no issues with that. However, when you talk about physics, it's important to define terms. So in these aspects, it was actually not simultaneous. What do we mean when we say simultaneous? What does it mean in the confines of physics and astronomy and science in general? It means that one event cannot influence another. This is what simultaneous means. How do you mean it? Well, because there is a limit. The limit is the speed of light. So if event A happens before the light of event A has reached another event, event B, then we call it simultaneous, as they have no way of influencing each other. This is what we call simultaneous, or at the same time, because time is relative, as we know. So we call this simultaneous. And if you think about it, for example, when I in Austria, I don't know, when I in Austria, I drop a stone, and a person on the other side of the world, which would be in the ocean, but let's say in somewhere in Brazil, for example, also drops a stone, and the time in between is less than it would take for a beam of light to reach from the one location to the other, then it's called simultaneous. There is no way that one of us would possibly have received the information that the other has dropped the stone. So this is a bit complicated. Maybe I should outline it with a nice example. So on the y-axis here, we have time. Time is increasing downwards here. And we start with an event A. This is in red here as the event is now occurring. And there we have event B. Event B has not yet occurred. So the information that event A has happened is traveling between A and B at the speed of light at best, right? Could also be, of course, at the speed of sound in case of the audio alarm from the example with Alice's phone. So the information has not yet reached event B. The information keeps traveling from A to B. Now event B occurs before information of event A has reached event B. And after that, you can see here that information from event A travels towards B, and information from event B travels towards A. None have reached each other yet, thus clearly they happen simultaneously, even though from our observational point of view, they haven't happened at the same time. Now, that seems somewhat silly. So it doesn't happen at the same time, right? Why then do we call it simultaneous? That's because we were stationary in this example. However, nature isn't always stationary, quite annoyingly. We have what's called moving observers. So you could, with any of these things, construct a moving observer that receives the signals simultaneously, and now I mean simultaneously as in the same time. This is what I mean. Just because we are stationary here doesn't mean that an observer moving at a given velocity in between A and B would not receive them at exactly the same time. And I mean in the same time as he would receive both signals at once, is what I mean here, right? This is the problem. This is what I mean here by simultaneously, at once, at the same single time, right? Because we don't know who is moving, we need to make we need to give the definition of simultaneous a little bit more room, because we don't know if anyone could be moving. We can't assume that someone from another reference frame isn't moving. And because we don't know that, we need to give a little more generosity to the definition of simultaneous, because time is subjective. We can only say it's simultaneous if they have no way of influencing each other. That's what's called simultaneous. For example, which is a very, very, very nice example that I like to cite, the birth of, should he be a real historical character, Jesus Christ, and the supernova that occurred, that we got the first signal of in 1054, out of which the Crab Nebula formed, M1, Messier 1, formed, were simultaneous, even though by our reckoning there are so many years apart from each other. But since information, since this supernova is so far away, information from the one event has not reached the other event before it happened. This is why we can call it simultaneous, because there is an observer moving at a given velocity for whom it occurred at the same time, at one time, simultaneously. The complicated way of formulating this is this GIF down here, and that's complicated for a layman. That's still easy for physicists. I read one of the general relativity books that I used to pass my general relativity master's course, and it was extremely complicated. I don't want to talk about it. Okay, so you can see that when the coordinate system is normal, when it is not stretched, at the velocity of 0, all of the events occur at one time. At a velocity of 0.3 c, and at any velocity that is not 0, the events will not happen at the same time anymore, and then you need to ask the question, well, could they influence one another? Okay, now the train example. Now that you know what simultaneous means, now that you understand why this is a thing and why we talk about it, let's talk about the train example. So let's say we have Alice down here as a stationary observer relative to the train, and then we have Bob on a train moving towards the left of the screen. Now lightning strikes, of course, twice, as it does always, at the same distance to Bob. So one happens at, like, I don't know, 100 meters in the front and 100 meters in the back, relative to Bob at that exact moment. Now, first of all, let's clear up the easy thing for Alice. Of course, they also happen, the lightning also strikes at the same distance to Alice. Alice hears both of these at the same time, so simultaneously. Clearly. In general, these lightning strikes are simultaneous. One signal could not reach the other before the other event has occurred. So this is simultaneous. However, for Bob, things are more complicated. Now, at the first time up here, the lightning strikes, Bob moves, no worries at all. Now, then these slightly pink, I think you call it, or magenta or something, signals travel at the speed of light. Now, obviously, none of this is to scale, and I'm not taking length contraction into account here. I'm just trying to get to the simultaneous point, right? The length, because I'm assuming that the lightning strikes at the exact straight path, the length contraction would be the same above, in front and behind the trains. It would not change this result, only quantitatively, not qualitatively. Let's keep on going. Bob moves at a given velocity, and the signal now from my drawing here, this velocity may look like it's faster than light, but it's not. It's slower than the information of the light beam. Bob moves towards the one signal and away from the other. Now, this signal here will reach him at light speed, because this is the maximum speed it has. Those two velocities, the one from Bob and the one from the light, are not to be added up. This is one important point of relativity. The speed of light is the fastest something can go. However, Bob moves away from the other signal, meaning that the signal that comes from behind reaches him with less than the speed of light, which you can see here. Bob moves into one, away from the other, thus the front signal will hit Bob before the second one does. So the bomb, in his example, the way I understood it, only explodes if it receives two simultaneous signals, but it doesn't. The one signal is registered before the other one is registered. The information of one reaches the receiver before the other. Thus it is not simultaneous, because the bomb is in the moving frame. Thus the bomb would not explode, of course, omitting any technical details about reaction times of actually technically existing receivers and things like that. This is a purely theoretical point, of course. Don't put bombs on trains and try it out, please. I don't want to go to prison. Okay, so with that, I think that's the video. I would like to emphasize this point, because I love it when flat earthers say, no, obviously not. but relativity is taken into account in satellites. It's taken into account in for example, particle accelerators. It's the knowledge about relativity is relevant for X-ray machines, for example. If you have the misfortune of experiencing cancer, sometimes the radiation therapy there is, for example, carried out with an ion beam, and you need relativity for that, or otherwise it just wouldn't work. Relativity is a part of our lives, and I think it's so funny that flat earthers say that, nah, it's not a thing. So I think that the takeaway message is the one that we have come to multiple times. Yeah. With that, I will leave you. I thank you very much for watching. If you enjoyed this video, maybe consider leaving a like. If you enjoyed this video a lot, maybe considering subscribing. And yeah, with that, I will leave it at that. I think I will see you in the next video. Until then, have a nice time. Goodbye.